Hello, I'm Alan. I'm going to be doing the Aero 340 recap video for February 19th, 2020. We first talked about the Runge-Kutta fourth-order differential equation, also known as RK4, versus Euler's first-order equation. The Runge-Kutta fourth-order equation can be found in MATLAB with the ODE45 command and uses up to the fourth-order term in the Taylor series. As you can see, if we have the Taylor expansion, the first-order Euler equation only goes up to the first term, first derivative, while the fourth order goes up to the fourth derivative. Because of this, the error of the Runge-Kutta fourth order differential equation is on the order of delta t to the fifth power, which is considerably less than the first order Euler equation. Given y prime of I, the derivative of the true equation, the Runge-Kutta can take the form of this. Y of I plus 1 is equal to yi plus 1/6 k1 plus 2k2 plus 2k3 plus k4, where each k is a constant, which is as follows. These constants are used to calculate as a weighted average in order to estimate the change of the true function over a certain delta t. The benefit of numerically integrating is that any differential equation can be decomposed into first-order differential equations and be calculated numerically. However, there are still many considerations to be thought of. First is truncation error. Large step sizes may not capture the true curve accurately. Error is directly related to the step size delta t, so too large will cause too much error. Secondly is round-off error. Computers only hold numbers to a certain precision. If the step sizes are too small, round-off error increases by rounding off too many numbers. Third is stiffness. A stiff system can be identified with widely varying time constants. If high-frequency motion is mixed with low-frequency motion, it becomes difficult to simulate the high-frequency motion without round-off error of the low-frequency motion. Examples being space stations in orbit and violin string vibration on the back of a pickup truck. Fourth is the computational time. Especially in real-time applications, integrating complex equation motions take time. However, it would be impractical to predict 1 second worth of motion after 60 seconds worth of calculations. So the speed of the algorithm is very important. Finally is the stability of the problem. Unstable problems have errors that propagate without bounds and lead to infinity. Some algorithms are stable, so the error is bounded. An example of a stable algorithm is the Runge-Kutta fourth-order differential equation. Finally, there are a few ways of checking whether or not the numeric integration is accurate. First, it is to compare it to real values or analytic solutions. This is a very direct method. If we have a true solution and our estimate, we can directly compare them to see the error. Two is to check the conserved quantities. These values should be constant at all time, so any fluctuation in these constants would signify inaccuracies. Third is to recognize if the system is stiff. If the system is stiff, we would need to reanalyze the equation of motion or use special algorithms that handle stiff systems, such as ODE15.